session. So next slide. Yeah. As we all know, RBC is Canada's largest bank with almost $1.5 trillion worth of assets, and we have more than 85,000 employees providing services in personal and commercial banking, wealth management, capital markets, and more. And as an organization, it is very important for us to keep up with the latest trends in AI and technology in general. And it helps us provide a smooth experience to our clients and customers. Uh, we have seen AI make good leaps and bounds in recent years, and this is primarily due to an increase of data, advancement of algorithms, improvements in computing power and storage. As AI continues to evolve, RBC is working on some really exciting projects, and we are bringing AI into the mix of how we do business. Next slide, please. So JSOC stands for Joint Security Operations Center. We are in charge of tackling special projects that improves the overall security posture of RBC. JSOC is divided into 4 teams, and each team has an unique role in expanding organizations' understanding of its security. First up, we have Adversary Emulation. This team is best known for emulating a sophisticated threat actor who is targeting RBC in attempting to achieve a specific objective. So they document their findings and explain how we improve our security at RBC. They also automate the testing of endpoint security tools and to evaluate the effectiveness of these tools. So they try to see what these tools are catching and what they may not be catching, and they try to find the best configurations for these tools. Uh, the purpose of threat hunting team is to proactively look for suspicious behavior within the network. Simply put, they set up honeypot the hackers in so that they can profile and analyze what kind of threats can the organization expect, and they develop defense strategies accordingly. Uh, Next, we have application development team, and as the name implies, development team collaborates with other JSOC teams and help pushing our work to production. And finally, we have analytics. So Nikhil and I are part of this team, and we provide data-driven solutions in cybersecurity. Uh, uh, and this is done with the help of data science. Our goal is to use machine learning and AI to analyze and detect cyber threats within RBC. Next slide. Yeah, a bit about my team. So the team consists of data scientists from diverse academic backgrounds. We have people who have done their PhDs in astronomy, biotechnology, neurology, physics, mechanical, and computer science. Uh, our job is to understand the existing business processes, identify the underlying problems, and then develop a solution to streamline these processes. The unique trait of our team is the exceptional business impact we deliver to RBC. Uh, so the bottom line here is it doesn't matter what background you have. If you are good at analytical thinking and you have a bit of a coding experience, then you're ready to be a data scientist. Next slide. Yeah, and finally, a bit about me. I'm a full stack data scientist in the team for more than half an year. I'm a Python and Apache Spark expert. So building custom big data solutions and efficient data pipelines is my niche. Some of my hobbies are coding, hiking, and I'm a huge Star Wars fan. So a fair warning, you'll see 1 or 2 Star Wars memes in the slides. So, okay. Now I'll let Nikhil introduce himself and take over the presentation. Over to you, Nikhil.
Sure. Hey, everyone. I'm Nikhil Sapru. I'm a data scientist in the team, and I focus more on building machine learning-based solutions to some of the use cases that our team works on. In my spare time, I enjoy running, biking, and playing squash. I guess it seems like there's an issue with the presentation where I guess, Pawan, I would share this, I would change the slide, but you probably saw it a few seconds later. So when I'm talking, if the slide hasn't changed, just let me know, and I'll wait until it does. It seems like there's a lag here. So I'll start off with a high-level overview.
Yeah.
AI is basically application of computational tools to mimic intelligent systems. And the idea is we're trying to build systems that have that can reason and actually make the kind of decisions humans usually do. That's sort of the grand goal of AI. ML in itself, machine learning, is a subset of AI that refers to self-improving technology or self-learning technology. And the main idea is, again, you're trying to mimic human behavior here, where you design a system that starts off at a certain level of knowledge, but as time progresses and it sees more information, it needs to adapt to that information and ideally get better with time. So within machine learning, deep learning is one form of machine learning technique that has gained a lot of popularity in the past few years. I guess in this slide, what I'm trying to show is traditionally, until a few years ago, the way machine learning was done was you had the first step used to be feature engineering, which was you had a domain expert who could also code, or a domain expert collaborated with a programmer to build a feature extractor who would take the inputs, pull out the relevant features, feed that into a model. So in this case, it's a classification model, and the model, after analyzing those features, would basically try to figure out, would make a decision. So in this case, it's trying to figure out if a tweet is polite or offensive. Now, instead of a tweet, if you had a car in this case, your feature extractor would basically try to, based on how it was coded, let's just say it would try to figure out, okay, if something has 4 tires and a certain geometry, it's probably a car. What makes this process a little bit more hectic and I guess time intensive is the fact that you would need to do feature engineering for different things that you're trying to design a system for. And that is sort of the time consuming and also the costly aspect. Deep learning, on the other hand, refers to neural networks, the use of neural networks for machine learning. And one strong advantage of deep learning is the feature learning or the feature extraction part is automated. You technically, as long as you have good quality data that represents the input in different ways, your feature extractor would ideally extract the relevant features for you and use that to make a prediction in the end. And that's where the power of deep learning sort of comes in, which is you don't need to develop this feature extractor for everything. So for example, if you have a car, a motorcycle, all you need to do is give it multiple images of the same class. And ideally, the neural network under the right conditions would learn the right features to do classification or any other task that it's designed to do. So this is an approximate chart, which sort of basically the goal, I guess, the message that's being conveyed here is deep learning is very data intensive. So it's very effective in applications where you have good quality data that the model can be trained on. You need a large number of examples. As a rule of thumb, let's just say if you're trying to classify images with like animals, for example, it's fair to say that you need at least a few thousand images ideally to be confident enough to say that the model will learn good representations. So a lot of learning algorithms pale in comparison to deep learning for their performance once the data set grows beyond a certain amount. So in this case, you can ignore the variables that sort of show up in here, and I guess the main idea is to give a high-level overview of what these models do conceptually. So this is a simplest form of a neural network. It's called a perceptron, and it has, as you can see, it has 3 layers: the input layer, the hidden layer, and the output layer. So the input layer is where basically you would figure out, let's just say if you had an image, you would pre-process your image a certain way, feed it into the model. The hidden layer is what will actually extract the features. And then these features go to the output layer, and then the output layer does the task that it's designed to do. So for example, if it's a classification task, it will try to classify what the object in the input image is. Next up is what you call the multi-layer perceptron. It's pretty much similar to the perceptron you saw in the previous image. But the difference here is it has multiple hidden layers. And these multiple hidden layers is what is sort of referred to in some ways as deep learning, where these are deep neural networks, and they're deep because they have a lot of hidden layers. Hidden layers sort of, you can think of it conceptually as a way to model complexity. And the more complex your input is, or the more complex is the system you're trying to model, you could assume that you would need more layers. And it has been shown empirically that models which are deeper will perform much better on complex tasks as compared to shallow models. Again, this is a very simple example of what you call a multi-layer perceptron. There are different classes of neural networks like convolutional neural networks, LSTMs, and transformers. But for the purpose of this presentation, we've chosen to keep it very high level and not go into too many technical details. So one of the reasons that one of the things that we do get asked sometimes is why is deep learning so popular, or why is it so popular right now? The interesting thing is neural network research has been going on for decades. What is different about this time is we actually now have large data sets available that you can train these models on. So large companies such as RBC, which is a bank, or a lot of tech companies, they actually collect a lot of data, and they've had it for a while. But another thing that has also changed is a lot of academic research groups, as well as research groups in the industry or some engineering teams in the industry, have put in the effort to actually build large quality data sets, good quality large data sets, and they've open sourced them. So even if you're a student or if you're a researcher who might not have access to actually setting up these data sets yourself, you actually have things available open source that can be used to work on your projects. And basically what that does is it gives a lot of people a chance to work on it. And when a lot of people are working, you would have more effective solutions coming out faster. The second thing that changed was the compute infrastructure, which is the interesting thing about deep learning is the same graphics cards that are very popular amongst gamers or even crypto miners. The same graphics cards are also very useful when you're actually training these deep learning models. And the reason is, compared to a CPU, the calculations or the compute that needs to be performed while training these models would run a lot faster on these GPUs. And what that does is it gives you results faster. So think about it this way. If you had to train a model and you had to wait a few months to get the results, you might not be as motivated to work on the problem, or developing a solution would take a lot longer. So when the reduction in the development time is also another thing that got a lot of people interested in working in this area. You could have something as simple as one GPU or a combination of GPUs, depending on the size of the data sets that you're working on. The pivotal moment for deep learning, I guess, was in 2012 when AlexNet, the neural network designed by a group of researchers at the University of Toronto, won the ImageNet competition. And this was sort of when, I guess, a lot of people in the industry as well as academia got to see that neural networks, when trained well on a large enough data set, could outperform a lot of the traditional techniques. And what basically this did was it basically got a lot of people interested in the area. So although a lot of people had been working on this, it was small groups that focused on this area. But after 2012, you had the number of researchers both in academia and industry working on this problem has grown very fast. And one example of looking at it is the popular neural network conferences. When you look at the attendance charts, you'll see the numbers have been growing exponentially year over year. And what that does is when you have more people working on the same problem, you have better quality at learning algorithms, as well as architectural improvements that have come out in the recent years that have further boosted the performance of some of the older models. So for the next 3 slides, what I'm trying to do is I'll just give some general examples where deep learning is used. These are examples that I believe most people can relate to. I think other than the 3 things that I mentioned earlier, I think one fourth thing, and that's a recent trend which has been happening out in the last 3 to 4 years, has been research groups, both in industry and academia, open sourcing their models. So what that means is, for example, if you look at the top left image, that's an object detection model called Detectron. This model was open sourced by Facebook AI Research back in 2018. So anyone can sort of take this model and use it for object detection. What that means is you don't need to actually do the training yourself and tune the models. And let's just say, even if you did not have access to the right compute infrastructure to train these models, as long as you're working with data that's very similar to the model, that's very similar to what the model was trained on, you could use this model and do some good quality downstream tasks as well. It can get tricky if you're trying to do the same thing on a different data set, because these models are highly sensitive to what they were trained on. But the fact that you have models like this and some others which are very openly accessible to people to play around with, that has also driven a lot of interesting applied projects where people have taken these models and built some really cool systems out of it. The other popular example that most people seem to be familiar with is open source self-driving cars. So on the top right, what you see is a data set that was open sourced by Waymo, which was formerly a part of Google. And this is the part of the company that used to focus on self-driving research. In this case, this is an example of what you would see from a LiDAR data. So LiDAR is the sensor on top of a lot of self-driving cars. Again, some companies choose not to use it, but this is a popular sensor which sort of maps the surrounding the things in the car's proximity. And this is one of the inputs that goes into the model to figure out what's around the car and what the next move should be given the car's end goal. Another popular example is generative models. So generative models is you train them on a certain distribution, and these models will basically try to generate similar data, which is very similar to what they were trained on. So an interesting application of that is the bottom left image that you see, where you have things that are scratched out, where you have someone's image, but parts of it are not visible. Assuming you have a good quality generative model that's trained on a similar data set, it can do a pretty good job at generating realistic images from incomplete ones, which you can see in this case. So if you look at the facial image in this case, you can clearly tell the model really understands how the transitions work in a human face. And I guess even with about, I would say, 30% of the face blanked out, the model was able to do a good job. Now, if the same model was not trained on a facial data set, it would probably come up with something else which would not look like a human face. So again, I guess the message I'm trying to drive here is it's very sensitive to the kind of data that the model is trained on. And the bottom right is sort of the last example, which is called neural style transfer, where you have this one image of some homes. You take this painting, and basically whatever the painting style here is, you sort of transfer it to that image, and this is the output that you get. This can be a cool hobby project, but again, this could have some interesting applications in the industry where you're trying to generate some images and you don't really want to paint things up or draw things up from scratch. The next example is deep learning applied to language. So which is again, in language is basically what you would also call natural language processing. I guess the first example that always comes to my mind is search. I think, we try to come up with complex search terms, but like the more complex your search term is, you might see that the quality of results is not as ideal. Whereas for simple search terms, it's usually pretty good. So in 2018, Google open sourced this model called the BERT, and the BERT is basically what you call a bidirectional transformer. And this is something that is pretty much the model of choice for a lot of language tasks right now where deep learning can be used. So one of the blog posts that came out of Google sort of show the before and after, where you put basically, a not so simple query earlier before they started using BERT. The top result is not what you would call something which is very valid. But after using BERT, what they're trying to show is that it's more sensitive to the kind of questions that you ask, and it usually gives out better quality results. Some other tasks are sentiment analysis. So sentiment analysis, if you ran a small business or a mid-sized business, for example, selling consumer products, you might have people leaving reviews on your website. And sometimes, it's not, once you grow beyond a certain size, it's not always possible to know what people are saying or what they're thinking about. And you don't want to manually read stuff. So this is a very popular example which a lot of business owners could use. Earlier, you had to do a lot more work to build out these systems, but with the tools available right now, I think it's relatively easier to deploy these things by different people. I think the third and a very popular example also is machine translation. So if you used Google Translate, for example, back in 2011, 2012, compared to now, you might see there's a very big difference in the quality of outputs that you get. And again, that's thanks to neural networks. And the last thing I would like to touch on is question answering. This is, again, another very popular application where you train your model on a corpus of information, and the idea is when someone asks an question related to that, you should come up with good answers. One popular application is question answering. And with question answering, I would say chatbots are, again, the most popular application that I can think of. A lot of the systems, especially when it gets more complex, what you're trying to do is you might have a human in the loop. And what that means is if your question system stops, if the system cannot come up with good answers within a few tries, you go to a human operator. The last example that I have is deep learning applied to speech, which is basically speech to text is the most common example. Again, most of the development that you see in improved speech recognition systems over the last few years comes from deep learning. The next example I can think of is speech authentication, which is, let's just say, when you call a lot of places for customer support, for example, they might basically ask you personal information to validate you. this is slowly being replaced by them storing a digital voice print of yours and authenticating you that way. A lot of the systems behind the scenes might be neural networks in that case as well. At this point, I guess, I think so far it was very generic. I think at this point, I would like to present something that's specific to, I guess, banking. And one common example is check processing. So I think one thing that's changed in the last 1 year, especially due to COVID, is a large-scale check process. Is basically, a lot more people that might have come to a branch or maybe gone to an ATM to deposit their checks now do it through the banking app. And in that particular case, what you're trying to do is there are multiple ways to look at this problem. But one way is you can look at it as an image segmentation problem. And by segmentation, what I mean is you pull out the relevant parts of the check. So in this case, it would be who you're trying to pay, the amount that you're trying to pay, and the amount in words and the amount in figures. And one interesting thing that you can check for is the amount in words versus the amount in figures. Do they actually match? And if that is the case, it's a simple case. And it's a simple case where the check could get cleared. But if that doesn't match, then there are certain other steps that might come in. Maybe you would need a human expert to come in and figure out how to deal with that check. This is, again, one of those things where, for a lot of straightforward cases, it's repetitive tasks that could be automated. And a human operator might not be the ideal person because it can get very boring for them. But for more complex cases where a system cannot right away identify what the issue might be, that's when you bring in the human experts who understand, checks a lot better. The next slide I have is it seems like a fairly straightforward case when I talk about check processing, but when you're actually building a production level solution, there are a lot of challenges and edge cases that you need to consider. So for the specific case of checks, I guess one issue that you're dealing with is different designs and templates. And what I mean by that is the same banking institution will issue checks which look different. Some people might get a plain check, some people might get a different color, some people have logos. You also have the option to go print out custom checks. Personal banking and business banking might have different styles. And what your model needs to be is sensitive to all these different needs. Some checks are handwritten, but let's just say the checks that, like a refund check that you get from the CRA, for example, it's actually typed out. It's not handwritten. So there's a lot of different inputs that can go to the model. And the idea is to build a system that is sensitive to all these subtle changes. Now, the interesting part is the human eye knows what to focus on and what to ignore. Machines are not very good at that. So there are some things which humans are naturally very good at. They can filter through the noise pretty fast. Unfortunately, machines are not always like that. So when you build these systems, you have to factor in these cases and make sure your system can address them. How check is written will also varies across nationalities and cultures. And what I mean by that is I grew up in India, and the way we write checks there is a little bit different compared to the way I've seen checks here. There's subtle differences, where how you terminate your check, how you write the figures, and your model needs to catch those. And I guess the interesting and the most challenging one that I've seen is corrections and edits. You can write a check and you can scratch something off. And then when you do that, you can just basically initial there. And your initial is basically your way of telling the bank that, hey, I wrote the check and I made this change. And as the owner, I'm initialing it to confirm that I'm the one who made it. But the reality is anyone can sort of take your check and do that, assuming they get their hands on your check, they might be able to do it as well and fake your initial. So how do you deal with those cases? So these are some of the edge cases where, the machine has to decide whether to let something go or bring an expert in. So for the rest of the talk, I guess we'll focus more on cybersecurity, and this is where Pawan will take over.
Awesome. Even at times, even I get confused between AI and machine learning, but I think you clarified it for me. But so thanks, Nikhil. So let's talk about cybersecurity for now. I think it is the most important topic for this talk. Whenever you hear the word cybersecurity, you would probably think of Trojans, botnets, network intrusions, right? But there's actually more to it. So teams involved in cybersecurity practices aim to maintain confidentiality and integrity of information management systems. Like conventional approaches to cyber defense basically monitors, tracks, and blocks cyber attacks. However, the vulnerabilities in these methods are ubiquitous. And with constantly evolving cyber threats, building defense systems for just discovered attacks is not enough to protect our users. Uh, it's it's about time we build proactive defense systems such that they can anticipate and eliminate vulnerabilities, and at the same time, they can defend effectively and rapidly against these attacks. Uh, Cybersecurity professionals generally rely on data to gather relevant investigative information to build these proactive solutions. But if you consider the amount of data we have at RBC, it's an impossible task to manually search and assess thoroughly and efficiently. Next slide, please.
Do you see the next
Uh,
slide?
I think, yeah, I can. Uh, it's probably already clear how the power of machine learning can be harnessed in cybersecurity. Uh, as we know, banks are always primary targets for hackers. So if you think about it, any cyber interaction with bank's network can be treated as good or bad. Uh, so this eventually boils down to a classification problem, and machine learning methods can learn from these patterns and estimate a classifier model. These models can help identify malicious activity and provide proactive recommendations on how to reduce the risk. And if you see this picture, this is exactly what it's like to have machine learning in cybersecurity space. Next slide, please.
You
Uh,
should see it.
yeah, I can see that slide. Here are some of the ways we can use machine learning in cybersecurity. Uh, the first one is misuse or signature detection. It's a mechanism which generates alerts when a known cyber misuse occurs. This technique measures the similarity between the input events and the signatures of the known intrusions. It basically flags behavior that shares similarities with the predefined pattern of the intrusion. This helps in identifying known attacks reliably and with a low false positive error rate. Next up, we have anomaly detection. So anomaly detection triggers alarm when detected object behaves significantly different from the predefined normal patterns. Uh, this is useful for detecting malicious activities. And in training process, we use machine learning to generate a profile of normal patterns. While detection, if the observed pattern deviates from this normal observed profile, it produces a large delta in the probability, and this can be used to flag such behaviors. The good thing about anomaly detection is it can detect previously unknown attacks as well. But at times you might have high false positive rates. But then again, it all depends on what kind of features you're using in your model. Uh, Scan detection generates alerts when attackers scan unauthorized components before launching an attack. It essentially identifies the precursor of an attack, and these techniques can be useful to detect attacks like data exfiltration, which is a, a really huge misuse which have happened in the past year, I guess. And profiling modules helps us cluster aggregators and benign users into different buckets. The term profiling used here is different from the one we used in anomaly detection. Here we focus on grouping similar behaviors to find the trends that these behaviors follow. Uh, Finally, we have fraud detection, which is the most common use case for financial institutions. It is used to protect customers and employees of banks from potential phishing attacks. I'll explain more with a scenario in the upcoming slides. Uh, Next slide, please. Yeah. Based on the aforementioned techniques, these are some of the use cases that JSOC deals with at RBC. A major chunk of our use cases are focused on financial crime. We have phishing detection. We have digital risk scores. Digital risk scores are nothing but I'm not sure how many of you are familiar with different kinds of phishing attacks. Like we have attacks like man in the browser, man in the middle, botnets, and etc. So for each type of attack, we have models which can generate a score, and based on that score, we determine whether this transaction is a man in the browser attack or not. And then we have IAM. So IAM stands for Identity Access Management. It is the process of identifying, tracking, and controlling employees' access to the information systems and applications. So IAM is a cybersecurity practice which every organization follows, so that we make sure that we don't have like employees have the right accesses, and uh, they don't have access to tools which they aren't supposed to have in the first place. So we have some models within IAM like role mining. So role mining model, what it does is based on your job title and your business responsibilities, the model automatically assigns you a set of accesses. So and you I think that would basically would be sufficient for you to do your business, your day-to-day job. And next up, we have outlier detection. In this use case, we will actually try to see if whether if a person is having an irrelevant access to applications within RBC. Uh, Data guard within cyber is almost kind of similar to what I discussed in IAM. Uh, Except it is very specific to database applications. We also provide miscellaneous services like data as a service and machine learning as a service. As you know, we are a data science team and we have access to a lot of data sets. So we have these APIs where other teams can use our API to get access to some of the data we have. And similarly, we have machine learning as a service. Uh, Other teams can use our pre-built models, and they can fine tune the model according to their data by just calling our APIs. Um, yeah, next up, next slide, please. Yeah, okay. Before jumping into fraud detection, I will give you guys a walkthrough of phishing scenario. So let me just read out this slide. Just bear with me. So Rebecca lives in Toronto and makes a monthly e-transfer to Mike, her personal trainer, for his service. They are patrons of same bespoke active gear retailer. Occasionally, Rebecca will transfer funds to Mike so that Mike may purchase fitness gear on his way to the studio. Next slide. On 7 January, Rebecca receives a text message offering her a 70% loyalty discount on Mike's training for the next 4 months if she logs into her RBC account and makes a payment immediately. While she certainly deserves a discount as a valued client, excited Rebecca is now a victim of fraud actor in Regina who is going to attempt to transfer several hundreds of dollars from her account to the attacker's own account. Now, this is how hackers get access to your bank account. They generally contact targets by email and text messages posing as a legitimate institutions. These email and messages contain website links, and when you click on them, they redirect you to a fake web page. This enables attacker to hook onto your connection with the banking website, and as soon as you log in, the attackers have access to your credentials, and they use these credentials to transfer money to their own accounts. So the ultimate goal of phishing revolves around scammers tricking users into giving up data and access to the systems. Next slide. So, how do we detect such fraud incidents? So here we actually leverage graph analytics in combination with machine learning. Uh, Despite using sophisticated fraud detection tools, which often uses basic machine learning concepts, businesses lose more and more money to fraudulent schemes every year. Uh, graph-based models can turn this pattern around. So, by establishing a graph model to our data, it just gives you a more insight into the data. So whenever, let's say I'm transferring money to Nikhil, so we can represent this as a nodes in our graph, and we can establish a link between me and Nikhil as a by which can represent the transaction, and this can represent how close we are in this graph. So so the nodes represent entities like you and me, and the edges represent the transactions, and the graph provides a natural way to understand these links. So let's say we have a phishing attack, and there's a lot of money going into a particular account. So that's often what we see in our data as well. Like attackers try to send money from different accounts to a sinkhole account, and so as you can see, there's a lot of money going in, but there's no money coming out of that particular node. And this, if you see it in the graph, it appears to be an anomaly, and you can say that this particular node is involved in some kind of fraud, and we can investigate further. So that's how advanced graph analytics helps here, because it digs deeper into the information rather than just using a tabular data. Uh, so the way we train such models is we have a tabular data. So here we have training data, and then we combine the graph features. We enrich this tabular data with the graph features, and then we train a model on it. And then for testing, we do the similar thing. We just enrich the transactional logs with the graph data, and then we feed it to the model, and the model predicts whether this transaction is fraud or not fraud. And a quick note here on the performance. Basically, uh, we don't see a lot of fraud cases in uh, because uh, it's the percentage of fraud transactions happening is very low, and we have an imbalanced data set. So we would use performance metrics like F1 score to measure how good our model is performing. uh, so yeah, next slide please. Yeah, and finally, I would like to discuss a few points about moving into production. uh, as you know, like being in data science field, I hear this a lot that data science is 80% data cleaning and 20% building model. Uh, I agree to it to an extent, but I think it only belongs to data science models which are built in academic backgrounds. But when you're building models for an organization like RBC, the actual reality is it is 20% cleaning, 20% feature extraction, 10% building of model, and 50% of building an efficient model. Uh, and when I say efficient model, there are few factors which comes into the play here. So there are limitations when you move your model into production. So you need to train your data on a regular basis, and it's not always efficient if you're making some uh, if you're not good at joining your tables in the right format, because we're dealing with like millions and millions of data here, and we use big data, and there's a lot of computation power, and there's also a cost associated with it. So things like so when I say efficient model, you should also think about how cost effective the solution is. And the other thing is like the accuracy of the model. uh, You don't need you don't necessarily need the model to be like 95% accurate, 99% accurate. The model can be 60% accurate and still deliver a business value to the team. So because this has happened for some of the use cases which I dealt with, the model performs like 60-70% accurately, but and it is still good for the business team, and that's what the business actually need at sometimes. So things like this comes into the play, so like optimization, cost effective, and the limitations of computation power on a regular basis. So yeah, these are some of the few points I would like to discuss on the production side. And now I'll just pass it over to Nikhil, and he'll give some tips on the regarding this.
So everything that Pawan described earlier in terms of model development and deployment, you could think of that as a first iteration in the model development process for production. And what I mean by that is you will train a model, and when you deploy it, that's just the beginning in some ways. So your model will, your underlying data will change over time. There might be other changes which will make your performance go down in time. So this is what you refer to as model drifting, which is a degradation in quality of predictions or any other task that the model is designed for. And when something like that happens, there are some things which can be figured out easily in an automated way, but there are some cases where you have to dig deeper to understand why is the model not performing well anymore. And a lot of times the causes could be classified into three buckets. One could be gradual, the other is seasonal, and the third is what we would call a black swan event. A gradual trend would be like, something that changes over time. So let's just say if you have a forecasting model that tries to predict how much of a certain product people might consume. There are trends where over time, where during a certain period, some things might get extremely popular and people are having a lot of that. But then after a while, that changes. And what basically changed is the underlying data. If you had been retraining these models, you would have captured that earlier. And that's why you also need to set up triggers where once you reach a certain performance change, you start investigating or maybe have an automated strategy to retrain the model. The other thing is what you might refer to as seasonal. Let's just say you are in a business which is seasonal in nature. For example, you see a lot more sales during the holiday season as opposed to the rest of the year. If you train your model on the average data or like the full year data, it might learn to figure out the features which correspond to different times of the year and do a pretty good job irrespective of the season. But if you're not encoding the seasonality in your model, in some cases, it might make sense for you to have two different models. Again, there's no clear answer for a lot of these. These are design choices that different teams make, and they figure out what's ideal for them. But again, these things need to be investigated when your model performance changes. The last one is what you call a black swan event, which is, call it a random act of nature, which is highly infrequent. And in some cases, you can say, okay, we can ignore this. This is something that happened. It won't happen again, so nothing needs to be done. But if that thing happens again, then you have to look at it, or I guess one example that I can think of right now is COVID. When COVID first started last year, I guess I was fairly optimistic that within a few weeks, it would go away. Again, I did not understand viruses well enough to know how fast it would spread. But what seemed like a black swan event to me at first is clearly something that stayed with us for a long time. And an interesting thing is, like, let's just say if you are a company that has, let's just say, both online business and in-store presence, one thing most of them would have probably noted is they're doing a lot more online sales as opposed to in-store sales. And if you still have models, let's just say back from 2018, trying to predict or forecast how much sales each channel would have, you'd be doing a pretty poor job at that right now. So you could have, for scenarios like this, there's two ways to deal with it. One is a manual retraining, and the other one is what you call a continual learning strategy. If you can identify trends in how the underlying data changes over time, or if you know what triggers to put in place to retrain your models, these are things that could actually be automated. If you're modeling something that changes very slowly over a long period of time, or anytime there's a change, there could be a multitude of reasons that cause it, and you need to investigate it each time. In cases like that, the manual strategy might be better. But again, it's very problem specific and team specific, and these are choices that you would make as a person designing the solution. One thing that you might have picked on during our talk is a lot of the work can be repetitive, or similar steps tend to be followed across different projects. So any good team, as a strategy to be more productive, you need to invest in the right tools. And tools, a lot of times, they might be open source. They might be something that you buy from a vendor, or in cases where your requirements are very specific and niche, which are not addressed by tools out there, you might go out and build that. Again, what tools to invest in, it depends on, it's a choice that every team makes based on what they're doing and what they think they'll be doing in the near future. The goal of our talk was at a high level to introduce some of the technologies that we use, how we use them, and what the life cycle of development looks like. We can move into the Q&A session, and we'll try to answer the questions that you might have for us.
Okay. For questions, I think, okay. Michael just asked, what's my favorite character? Um, I would say Han Solo or Ahsoka Tano. I just oscillate between the two characters. I don't know why. Uh, Next, we have Ajay. I'm sorry if I'm pronouncing it wrong. So, how is misuse or signature detection done before ML was introduced? So, we have a bunch of detection tools. I'm not familiar with a lot of these tools. I'm not a cybersecurity expert per se. So this actually comes under the adversary emulation and the threat hunting teams, and I think they would answer much better for this question. But uh, you know what? Actually, you can contact me on Discord. I'll just get back to you on this question afterwards. And you also ask, like, when did machine learning become the standard, industry standard for intrusion detection? I think we introduced machine learning in RBC. I mean, especially in the cybersecurity space, it was almost 3.5, 4 years ago. Yeah, right around 2015, 16 time, I guess. So, and then we delivered some good solutions, and since then, I think we are using machine learning for intrusion detection. Okay.
I'll try to take the next
Yeah.
one. I guess I can answer that.
Yeah.
Can someone get into financial AI without a cybersec or networking background? And the answer is absolutely yes. I don't really have a background, and I'm a new member in the team. I've been here a few months, and whatever I learned about cybersecurity is usually what I've learned after joining the team. So a lot of these projects are highly collaborative in nature, and everyone brings a certain skill set to the table. So depending on the team and how large or how collaborative it is, people will have different skill sets, and everyone does their part. There are definitely some people who have a very good understanding of different things that go into a solution. But a lot of us, especially at the entry level, the way we start is we can do one part of the job, and then you grow from there.
So Dave is asking, what is a graph model? Nikhil, do you want to answer? Maybe if you have an
A
experience.
graph model, again, I haven't worked much with, but like a graph model is what you would call a graphical model, where you basically represent your entities usually as nodes, and the relationship between them could be a connection. So that's one way to represent information. So I think graphical models are fairly popular in modeling social media interactions. Like that's one common example that a lot of people can think of. If I understand correctly, there's also like search engines can also use graph databases where you try to. I think at a high level, a graph model is what you would refer to as a graphical model, and it's basically a way of, I guess, storing and organizing information. And you could that's step one, and the step two normally tends to be there are certain advantages to it. I'm not an expert in graph models myself, so I can't really go into those specifics, but I do know there are certain scenarios where it's a lot better than using, let's just say, a relational database. It seems like we might be done with the questions for now. We could call it a day if there are no more questions.
Wonderful. Thank you everyone so much for joining our workshop today. Nicole, Pavan, that was a great presentation. If anyone else has any questions, please feel free to just put it in the chat and then we can send it over to the greats. But if not, we will go ahead and just close off. Thank you.
Yeah. Thank you, Betsy.
Thank you, Betsy, and thank you for giving us the chance
Thank
to
you.
deliver this talk. Take care.
Absolutely. Amazing. Thank you all. Have a good evening.